an invited talk to do. So we will finish the class a little early today. Okay, so as you understand that we are coming to the closing of the syllabus. So we are more or less done with the things that we had to do. And like there are only a few things left, which we will
Sir, what is
cover
the
in the
syllabus of the class
next,
test 3?
whatever I'll teach you till Friday.
So from the beginning.
From the beginning, everything is there.
Okay, sir.
Okay, so we will start with this new set of things. So this set of lectures will introduce you to uh, a special kind of a data structure. So so this is again a data structure facilitating search. So remind me, what are the different techniques of search that you have learned all through the Algorithm 1 course? Remind me some of them. We have done sequential search. We have done
Binary.
binary search.
DFS, BFS.
Yes, we have done DFS, BFS kind of thing. But these are on graphs. Okay. Um, Specialized search techniques on graphs. Then you have also done. Uh, why are you removed? Because I have made everyone. So I am the only presenter.
Sir, could you please make everyone attend?
Yes, sir. Now I think I am an attendee, but previously I was presented and I was removed from the meeting.
Sir, you are muted.
And then you have also come across specialized tree structures for search. For searching items like binary search trees. And AVL trees. Right? So all these searches, like so let us consider only those that search items and not search in graphs. So let us, for the time being, let us forget this. We are only talking about searching items, say from an item list or an array or something. So all these search techniques, there was one thing that was common. Can you tell me what? All the search techniques, technique wise, there was something that was common. Any thoughts on this? So let us try to think about sequential search. This will help you probably remember. So what would you do in a sequential search?
Sir, we
Check for
linearly check all the elements.
Yeah. So check means how are you checking?
With the key.
One by one, sir.
What do you mean by checking?
We are comparing the given value.
Compare. Okay, very good. Compare. What are you doing in binary search? Again, what checking means
Compare.
here? Compare. Right? What happens in these two cases? When you insert elements or
Compare.
search elements, compare. So,
Sir, in DF,
not
Okay.
DFS and BFS. We are not talking of these. Not the graph search techniques. We are only talking of item search. As I already said, we are not including this type of search on graphs, which is not typically item search. So, whatever item search techniques that you have learned so far are based on the idea of comparison. Okay. So all item search so far have been based on comparison. Now, today we are going to introduce ourselves to a completely different paradigm of searching. Okay. So here we do not really go for a comparison. Okay. We do not really go for a comparison for searching an item. So what do? We try to reference an item, okay, based on a key value. So this is the crux of the whole point. Okay. So reference an item based on some key value. So this means that somehow the items have to be converted to keys, and the referencing can be done on the keys directly. Okay. So this technique actually is introduces a new branch, a completely new branch or paradigm of searching, which is called hashing. Okay. So we will introduce ourselves to this important method of searching items in an item list. And as you will see that some of you who go forward and take interest in topics like data mining and cryptography, you will see that this idea is like extremely usable. Like it comes time and again in these fields. Okay. So data mining, especially when you are dealing with large data sets, or rather very large data sets. Probably some of you have already come across this term big data. Okay. So people among you who are interested in big data or in cryptography, you will see that this concept of hashing will come time and again. Okay. So now, what is hashing? Okay. So this is the first thing that we need to know. So hashing actually, as I said, is a technique facilitating search, okay, and it's a special type of search which includes two things: a hash function, okay, and a hash table. Okay, so these are the two important components of a hashing technique, okay, or the paradigm of search based on hashing. So what is a hash function? Now, a hash function, let's call it H, maps keys of a given type to integers in a fixed interval. Let's say, for the sake of argument and without any loss of generality, interval 0 to n minus 1. Okay, so it maps keys of a particular type. So this could be strings, this could be characters, this could be numbers. Okay, so this could be alphanumerics. So it maps these keys into a set of integers which are fixed. So this term fixed is very important here. Okay, so you map this into a set of integers which lie in a fixed interval. Okay, so we usually call hx to be the hash value of the key x. Okay, now some examples, some routine examples. Okay, so here this kind of hash functions are used when x or the key are integers. You could have multi-integer things also. So here the hash function depends on two different integers rather than one. There would be more. We will come to them slowly. Slowly we will unfold. Okay. Now, what is a hash table? A hash table consists of a particular hash function, let's call it H, and an array typically called a table in the hash table literature, okay, of size n. Okay, the idea here is to store the item ke at the index hk of the table. Okay, so you want to store the item ke at the index hk of the table. So this is a key and this is a value. Okay, so it's sometimes also called the key value pair. And you want to store the value of the item at the hash of the key location in the table. Okay, let's take an example, a very easy one to start with. Let's say we have hx is equal to x modulo 5. Okay, so let's say we have these 3 entries to put in the hash table. So definitely first thing to do is to compute the hash function for each of them. So since this is 6, so it will go in location 1, right? 6 modulo 5 is 1.
Yes, sir.
Mm. Okay, fine. So in this way, you can store the elements of the key value pair in the table along with the keys. Now think of a search situation.
Sir, what if we have 11 some
Wait. We'll come to all those things. We'll come. Yes, you have trapped the right thing, but let's go slowly. There are a lot of issues that we will come to. Okay, but now let's first think of the advantages. Then we'll come to the disadvantages. I think you are trying to point some disadvantage. Yeah, we will come to them. Okay, let's first think of the advantages. Think of a search situation. So how is it different from a comparison based search?
So here we just find the hash value of the given key so that we can directly go to that position of the array. So it doesn't need
Very
to.
good. Very good. So there is no comparison required. And what advantage does it bring?
O of one.
O1 search. O1 search. So
Sir,
in the comparison based search, you cannot do anything better than O log n, right? Whereas here you are able to do a O1 search. So the search is now, the search complexity is now order of 1. It is just referenced by the key. So as soon as you are given the key, you compute the hash and you go to that location and you retrieve the element. Okay, so it's a order 1 search. Anybody was having a question?
So, but we required order and time to find the hash values for the n elements, right?
Why?
To find the hash values of the each and
That's the
every.
construction. That's the construction time. That's a
Okay,
one-time business.
okay.
That's a one-time business. Once the hash table is constructed, you can always search in order 1. So there is a construction overhead also for binary search. Okay, sorry, binary search tree. So this is a data structure which is comparable to the binary search tree or AVL tree kind of data structures. There also you have a construction overhead which is order in log n. So similarly, you have a construction overhead here, but once the construction is done, the searching is facilitated in order 1.
Sir,
Yes.
if we have to search by key, then it is fine. But what if we have to search by its name?
You are never asked to search by the name. You only store the keys. Okay. You only store the keys. So there is a key value connection. We will look into this. There is a key value connection. You typically generate your keys. So this is a first example that we have seen, but you typically generate your keys or try to generate your keys from the elements itself. Let's see how. So now let us see a first realistic example. Let's say we have n equals 5. Okay. And we have to store the phone book. Okay. Now let us say my hash function h is defined as hw, which is length of the word w modulo 5. You see how I am using the element itself to generate the key?
Yes.
So now let's say we have these 5 positions. Where will Alice map to?
0.
0, 0.
Where will John map to?
4.
And Sue to, sorry, 3.
So, but the
Okay.
hash function shouldn't always be injective.
What does that mean? Why do you want it to be
I mean,
always
that means
injective?
so that two different elements don't have the same.
I'll come to that. I'll come to that. Let's wait. Somebody else also asked it. Asked the same thing. We will come to that problem. We will come to that issue. Let's wait for a while. And suppose along with this, we are also storing the phone number of that person. So you can store any other stuff as long as you know how to map the keys. Okay. How to map the keys to their hash locations in the table. You can store any other item along with it. Okay. And typically your search will be based on the name list. Now, as somebody just now pointed out. So here, like finding an element, again, as we have convinced ourselves, is order 1. Okay. Now, somebody already, I mean, at least a few of you already have observed this problem. The problem is what we call in the hashing literature collisions. Okay. What if you have to store Joe? Okay. This will collide with okay. So therefore, this hash function is a very bad hash function in general. Okay. So even if we make n very large, let's say n is very, very large, then also this is a very bad choice. Can you tell me why? even if n is very, very large? Can that avoid collisions?
No, sir.
Why?
Sir, because string of same length will be pointed to the same
Will be
key
always there.
value.
And like if I make n very, very large, what it would only do?
Sir, it would expand the key range.
No, not really. I mean, why does it not suffice to increase the length of n?
So we have fixed the size of the interval. So fixed number of integers.
No, no. Suppose I give you like enough space, n is getting larger and larger. Think. These type of questions are very important to
Sir,
think.
since
Sir, a
in
lot
general
of
names
empty
are short,
space.
Excellent, very good. So most of this n that you increase will remain unused, right? That's what you wanted to say, right?
Yes, sir.
So these names are like, typically think of the like word length for any name. Does it go beyond say 8 or 10? Hardly, right? So all of them will clutter on these 10 positions, whereas the rest of the n will remain empty. So this choice of a hash function is not a good choice. So then let's go to some other example. Let's take our second example. Let us see if we have called this as example 1 so that you remember better. Okay, example 1.
Sir,
Huh.
sir, but choosing n as a very large value, sir, it
Uh,
can also help us in uh, resolving the collisions a bit.
how?
So because suppose here in this case n equal to 5, so 1 and so word length of 1 and 6 are mapped to the same value. But
Yes.
if n is greater, then this will not be the case.
Suppose, so say the word length w, okay? Word length w. So what are the typical uh, like name sizes that you can think of?
10.
10. Okay. So this is less. So w, let us assume, is less than equal to 10. Okay. Fine.
Yes, sir.
Now then, tell me, like if I make n 10,000, does it help?
No, sir. And beyond 10 will not help.
That's what I'm telling. That's what I'm telling. N beyond 10 will not help. So if you arbitrarily increase n, unless and until you are judicious about choosing the hash function, this will not help.
Okay, sir.
This is what is my point.
Yes, sir.
Okay. So that's why, like, you have to be, as I said, you have to be judicious. So one way to be, to think about, say, having a judicious choice would be to consider, say, the social security number. This is for the US setup. You can also think of the Aadhaar number in the Indian setup. Okay. Now, what you can do here, let's say we have n equals 1000. Okay. And my hash function is, say, the last 3 digits of the social security number or Aadhaar number, whatever it is. Okay. So then here again you can have
Sir, can you scroll up a bit?
Done?
Yes.
Mhm. So you can have a situation like this. But this still does not avoid collision, right? Does it?
No, sir.
It does not, right? Say for
Yes, sir.
instance, there might be someone like Tipsy, and in this case, again, there will be a collision at position 2. Okay. So therefore, we need two things. We need to be judicious about two things when we decide a hashing technique. What are the two things? The first thing is the choice of hash function. And the second is collision handling. So no matter whatever hash function you choose, collisions are inevitable. Okay, we will see this. And if there are collisions, we need to have mechanisms to what we call collision handling. Okay, so these are the two important things which needs to be taken care of when you design a hashing technique. Okay, the choice of the hash function, which is very important, as we will see, and in the next part of the lecture, and maybe from tomorrow onwards, we will see like the effects of collision handling. Now, before that, let us try to convince ourselves that collision is kind of unavoidable. So let us ask, how probable are collisions? We will try to motivate this using an example. Okay. So suppose there is a party going on where there are P persons. Okay. So what is the probability that at least 2 persons have birthday on the same day? First of all, let us proceed step by step. What is n here?
365.
365. Okay. So now let us compute. Let us say that Q of Pn is the probability for no collision. Okay. Then what will be this? If there is one person, if there is one person,
One. Sir, one.
if there are two,
Sir, n minus 1 by n.
Sir, if there is one person, should the probability be 0 or 1? Because there will be no collision.
what are we computing? Probability of no collision.
Okay.
So probability of no collision is 1. If there are p persons. Now, if you have calculators in front of you, tell me quickly that if I set p larger than 23, what is the probability of collisions? So probability of collision is 1 minus this. If p is set to be larger than 23, if anyone has a calculator, help me find out what is the probability of collision. If you compute this, you will see that this is already greater than 0.5.
Yes, sir. It
Okay.
is a trivia, I think.
Yeah.
That 23 people will have 50% probability.
Yeah, exactly. It's a trivia also. So this actually has lot of connections to the birthday paradox and things like that. Okay. So anyway, so you will see that as p becomes greater than 23, the probability of collision is larger than 0.5, and this after this it grows like very fast. Okay. So therefore, this is kind of a mathematical way of saying that collisions are unavoidable. So what can we do? So our try is to minimize or reduce the number of collisions. Okay. And these can be, as I said, this reduction can be effected by two ways. One is designing good hash functions and designing good collision handling techniques. Okay, so we will go one by one. First, we will look into mechanisms of designing step by step, designing some good hash functions. Okay, but there is a caution here. There is no end to this. Okay, I'll tell you like once we finish this part, I'll suggest you to read something up if you are interested in this. Of course, that is not part of the syllabus, but it will be good to know like what is a really good hash function. Okay, so first, suppose your key is an integer. Okay, if your key is an integer, you can just have as simple a hash function as this. Okay. However, if your key is, say, a long, okay, so long key. So then if I set hk is equal to int k, is this a good choice?
No, sir.
Okay. So this is not a good choice. So why is it not a good choice?
Sir, what about the numbers are only 2 but they are very large?
Yes, but yeah, but that will always be hashed, because there is a modulo in acting there.
Yes, sir.
That is not the thing. There is a more intriguing thing. So all these are happening in the modulo space. So remember that we are just talking of the function itself. There is everywhere there is a modulo n. Okay, but still, even then, even if there is modulo n, this is not a good choice. So the idea is that when you design a hash function, you should try to utilize most of the information latent in K. And if you are doing this, if K is long, and if you are doing a typecasting of int, so then you are losing half of the bits, right? So you are not leveraging. So this actually results in loss of half of the bits. Okay, and therefore you are not leveraging the entire information that is laden in the key. So that's why this is not a good choice. So what could be a good choice? One simple way is to say have a binary representation of the key. And try to use all the bits. How do you do that? One simple way, like you are free to choose. There are multiple ways. Hundreds of different ways could be possible. One heuristic could be, so these are heuristics, therefore. So one heuristic could be that you typecast the higher order bits and the lower order bits. And sum them up. Okay. Now what happens if it is a string? Say string S. So one possible representation could be that I say, okay, I typecast each of the characters and add them up. Now question is this a good choice? What is your opinion?
No,
Why?
because still there can be many different strings having the same sum.
Many collisions, right? This promotes a lot of collisions, in fact. Can you give me some example?
Yes, sir. Like start from A to Z and increase A by 1 and decrease Z by 1.
True.
So
So
all permutation on one string.
yeah, so
Out
true.
of
Some examples, some typical examples to help all of us think are just a simple change, a simple swap. Okay, these two will collide. Not only that, so you might say, okay, these are like concocted strings. Even real words appearing in English language will collide if you want to do a dictionary hashing. This is exactly what you just now said. All of them will collide. And all of them are valid English words. So then, one good way is to use polynomial hash codes, which is widely used in fact. What does this say? Suppose you have so we consider each position and let us name it xi. Okay. Now we define hk as x0 a to the k minus 1 plus x1 a to the k minus 2 plus up to xk minus 1, and of course otherwise this will be just a simple sum. Okay. So we set a value of a to be larger than 1 and we design a polynomial hash like this. Okay. And in fact, there are some experimentally well-known good values of a. These are some experimentally well-known good values, and these are actually used in Java and many other environments for their own hash maps. Okay. So these guarantees only 7 collisions. Choice of one of these guarantees 7 collisions $50,000 English words. Okay. Of course, this is an empirical observation. There is no theoretical proof for this.
Sir,
Oh.
50,000 words means like there are many words in English, so it's an average or
I mean, I don't understand. Average means?
sir, there are many means infinite amount of words in English. So out of
Randomly,
any
randomly
okay,
chosen 50,000
okay,
words
okay,
over
sir, yes,
multiple iterations. Over
yes, sir,
multiple
but
iterations. Okay. So now there is one more thing that is left to discuss. We have not talked about n so far. So in the design of the hash function, is n at all important? Is the choice of n at all important? So you are assuming that all of these were modulo n, modulo n. Okay. Everything was in modulo n space. Now, do you think that n, do you think that n should have any specific property, any specific special property? Suppose, let me motivate you by this example. Suppose my keys are as follows. And one choice is 100 and one choice is 101. Does this ring a bell?
Yes, n should be prime.
N should be prime. Okay, so our objective should be to choose a prime n, and this prime n will have a higher likelihood to do what?
Avoid collisions,
By
mapping them to different indexes.
so what is it doing? So that has an English word. That's why I have put that dash. This will help you remember forever.
Distributing.
Yes. Or better say, let me write it in red. Spread. So the objective of choosing a prime n is to spread the key values as much as possible. So increase the likelihood to spread the key values as much as possible over the entire hash table. Okay. So we'll stop here, and tomorrow we will discuss about like an algorithm to construct the hash polynomial, and then we will discuss about collision handling.
Sir,
Yes.
since all the keys are about 200, why is that special property for n to be 100 or 101?
Huh? So how many collisions will you have here?
So for every 100, we will have some 20.
No.
No, sir. We
Per point you will have 3 collisions. 0, 5, 10. Sorry, 5, 10, 15.
Sir, I'm not getting, sir.
Okay, let me write the other numbers. Then it will be clear. Since I have not written the rest of the numbers, so it is so how are the numbers coming? So each hash code, if you take key mod n, okay, so this is your hash function.
Then first we will have a collision at 200 and then at 300. In between we don't have any collisions.
We don't have any collisions.
The 205 and 305 collides. 210, 310
Think
collides.
about it carefully. We will take it up tomorrow. Think about it carefully. Each hash code will collide with 3 others. Think about it carefully. We will take this up tomorrow.
Sir, what is the last number you have written? Is it 600?
600.
Okay. Okay, sir.
Then, sir, for 101 also, many will collide 3 times.
Yes, sir.
Think about it. Think about it. We will talk about it tomorrow.
Okay, sir.
Thank you, sir.